In this video, we will be looking at how to solve simple trig equations. A lot of this will be familiar from grade 11, but it will be extended in that we will be doing everything in radians, and some of the equations are going to be a little bit more complicated than in grade 11. So first of all, when it asks you to solve for x, it just means you're trying to find the values of x within a certain domain that satisfies the equation, meaning the left side and the right side are equal to each other. Okay, let's get into our first example. Solve sine x equals negative square root of 3 over 2. And then we're given the domain on the right, which is just saying that x has to be between 0 and 2 pi. Now, when I see my ratio, I am thinking of my special triangles. And because it is a sine, I am looking for opposite to be square root of 3 and the hypotenuse to be 2. So I'm just going to draw my special triangle. This does remind me of the equilateral triangle that has been cut in half. So here it is. I want opposite, hypotenuse, and that leaves us with our alpha as pi over 3. So our related acute angle. That will help us find x. Now we are given a negative ratio for sine, and sine is negative in quadrants 3 and 4, if you think about your cast rule. And now that we know our quadrants and we know our alpha, we can solve for x. And this is a very grade 11 level question. So in quadrant 3, we are past pi, so we're going to add on pi over 3 to pi. We would get our common denominator, so that would be 3 pi over 3 plus pi over 3. Here's our first answer. And in quadrant 4, we're almost doing a full rotation, but not quite. So that's going to be 2 pi subtract pi over 3. Again, a common denominator, so 2 pi would be the same as 6 pi over 3. And when we do the subtraction, there's our second angle. Both of these angles fit within that domain of 0 to 2 pi. Now, something that we do have to consider, but not so much in this case, would be what the period of the initial function is. So when I look at sine x, well, there is no horizontal compression or stretch because the k value is 1, which means the period would just be 2 pi. So there can't be more than these two solutions, because if I were to go into a different cycle, I'm already past that 2 pi mark. So my final answer here is that x is equal to 4 pi over 3 and 5 pi over 3. Now let's go to our next one. We have 2 cos of x minus pi over 6 is equal to 1. Now this is a little bit more complicated than the previous question, so we can do a little modification to make our life easier, and that is, let's just replace x minus pi over 6 with theta, and then the rest of the process is going to look a lot nicer. So that means we are solving 2 cos theta equals 1. Now don't worry, we will bring back that x minus pi over 6, but temporarily we're going to make our life a little easier. And now we can isolate for cos theta by dividing both sides by 2. And this is the little equation we are going to solve. And again, when I see 1/2, I am thinking of a special triangle. Because it is cos, I want adjacent to be 1 and hypotenuse to be 2. So I'm going to go back to the triangle I drew. This is what I want, and that actually gives us the exact same alpha as in the previous question. So alpha will be pi over 3, and this time our cos ratio was positive, and cos is positive in quadrant 1 and quadrant 4. So that means theta is equal to pi over 3 in quadrant 1, And in quadrant 4, it's equal to 2 pi minus pi over 3, which is 5 pi over 3. Now, of course, the question wasn't asking us to solve for theta, it was asking us to solve for x. So we have to think back about that little modification that we made before. I'm going to go in and replace theta with my original statement. So instead of theta equals pi over 3, I'm going to write x minus pi over 6 equals pi over 3. And then I will solve for x by bringing that pi over 6 over. And while I do that, I will just get a common denominator. So I'll replace pi over 3 with 2 pi over 6. That's going to be 3 pi over 6, which does reduce to a nice pi over 2. So there's our first solution. And now I'm going to do the exact same thing with my other theta. So I will replace theta with x minus pi over 6 and bring it over again. And I'm going to get a common denominator at the same time. So 10 pi over 6 plus pi over 6 gives us 11 pi over 6 as our second answer. And I'll just put my little therefore statement at the top here. Therefore, x equals pi over 2 and 11 pi over 6. All right, let's go to our next example. And in our next example, our period will change, which will require a little bit more thinking and potentially some graphing to help us out. So we are solving the square root of 2 times sine of 2x plus 1. And once again, I have an angle that's a little bit more complicated than usual. So I'm just going to say, you know what, I'm going to let theta equal 2x. Let me make my life a little bit easier temporarily. And now I'm going to isolate for sine theta. So I'm going to bring the 1 over to the other side, and then I'm going to divide both sides by the square root of 2. And here we are. And once again, I need alpha, I need my quadrants. It's sine again, so opposite hypotenuse. When I see that square root of 2, I am thinking of my pi over 4 special triangle. So I will just draw that in, 1, 1, square root of 2. And confirmed, opposite is 1, hypotenuse is root 2. So alpha is pi over 4, and sine is negative in quadrants 3 and 4. So in quadrant 3, we're adding alpha to pi. With that common denominator, that would give us 5 pi over 4. And in quadrant 4, we're subtracting alpha from 2 pi, getting a common denominator. Our other angle is 7 pi over 4. Again, our goal was not theta, our goal is x. So I'm going to go in, replace theta with my original statement, which was theta is actually equal to 2x. So instead of theta equals 5 pi over 4, I'm going to write 2x equals 5 pi over 4. And to isolate for x, I can divide both sides by 2, which is the same thing as multiplying by a half. I am going to show this as multiplying by a half because it's going to look nicer when I have to apply that operation to my fraction. But they will both get you to the same place. Because remember, if you divide both sides by 2, dividing a fraction by 2 is like multiplying it by its reciprocal, which is multiplying by half. So here's your first option for x. It is 5 pi over 8. And I'll do the same thing to my other one. And again, multiply by a half or divide by 2. Same thing. And my other answer is 7 pi over 8. Now, these are not the only answers we have. So I'm going to go to my knowledge of base functions and transformations to do a little sketch here. And when I do my sketch, I'm just going to do my sketch for sine of 2x. For sine of 2x, the period is 2 pi divided by k, so 2 pi over 2, which is pi. If my period is pi, that means within my 2 pi domain, I'm probably going to fit 2 cycles. So I'm going to do a little sketch here, x, y, and I'm just going to do this for pretty much the base function, but that period has been compressed. Sine's going to start at the midline, and because my period is pi, that one rotation only takes up pi radians. I'll do a second cycle, and now I'm at 2 pi. It's a very rough sketch. Notice I didn't take the +1 or the √2 into consideration, but that's because I'm going to look at this equation here. Sine theta, or sine 2x, is equal to -1 over √2. If I wanted that as a decimal, I just punch it into my calculator, and that's approximately -0.71. So let's say it's roughly here. Now, if I draw that line across, I will see that within my domain from 0 to 2 pi, I have 1, 2, 3, 4 different answers. And the first two are the ones that we came up with. If I want the other two, because I have to present all possible values of x within this domain, well, those 2 points are the same ones that we have, but one period later. And the period is pi. So to get my other two x values, I need to add pi. So another option for x is going to be 5 pi over 8 plus pi. Thinking of the common denominator, pi is just 8 pi over 8. And when we add those up, that's 13 pi over 8. So there's my third option. And my fourth is 7 pi over 8 plus pi. Again, common denominator. That's going to be 15 pi over 8. So we have 4 different answers here, and our sketch helps us see that. So I will write, therefore, in order for the left side and the right side to match within the domain that was given to me, x can equal 5 pi over 8, 7 pi over 8, 13 pi over 8, and 15 pi over 8. And these first 3 examples that we did not need a calculator for them because we were given ratios that were part of our special triangles. But sometimes a calculator is involved and we have to find alpha with a little bit of an inverse, but otherwise the process is the same. So let's try 2 more examples here. This time we will need our calculators. If we look at example 4, you will see that this equation has sine x and cos x. So we are going to have to use a trig identity here. But before we do that, I'm just going to bring this 2 cos x to the other side. And now, I can't solve this trig equation with 2 trig functions, so I need to think of an identity that might fix this problem. And one that's jumping up at me is that tan x is equal to sine x divided by cos x. So I could make this sine turn into tan if I divide it by cos, and if this were divided by cos, well, that would just be 2 times 1, which would be excellent. So I'm going to divide both sides by cos x, and that is perfectly fine because I'm doing it to each side. And that will leave me with 3 times tan x equals 2, because the cos x over cos x is just a 1, and the sine over cos is tan. And now we're back to basics. I'll divide both sides by 3, so here is the equation I am solving for. There's nothing weird with our period because the angle is just x. So we won't have to do any of that adding of the period like we did in the previous example. I just need to find alpha and write down my quadrants. And the ratio of 2 over 3 is not part of the special triangles. So to find alpha, I am just going to take the tan inverse of 2/3. remembering that even if that ratio had been negative, I would still be taking the inverse of a positive ratio because alpha is always in quadrant 1, where all of the ratios are positive. So alpha is 0.59. Tan is positive in quadrants 1 and 3. So in quadrant 1, x is 0.59. In quadrant 3, pi plus 0.59. So that's going to be approximately 3.73. And those are our two answers for this equation. And this is an example where knowing those identities from grade 11 could be helpful because we turned something that looked a little complicated into a much simpler equation. All right, example 5, I do have cosec on one side and cosec on the other, which isn't as scary as example 4 because I can just move some things around and collect like terms. So I'm going to bring the cosec to the left and the 5 to the right. And I'll be left with 13 cosec minus cosec equals negative 5. Remember, there's an invisible 1 in front, so I can collect these like terms. And now we're back to normal. Let's divide out that 12. And here is the equation that you are solving. And I am going to need my calculator for this. So I'm going to take the cos inverse of 5 over 12, the positive ratio, because I want an acute angle, and alpha is approximately 1.14. And in my equation, cos has a negative ratio, and cos is negative in quadrant 2 and 3. In quadrant 2, it's going to be pi minus 1.14, which gives us approximately 2. And in quadrant 3, it's going to be pi plus 1.14, which is going to give us approximately 4.28. And in this function, because my angle was just x, there was no k value other than 1. The period was 2. There aren't going to be more solutions. So x equals 2 or 4.28 within that domain. And that's it for solving some simple trig equations.